and welcome to the wolfSSL live webinar, Open Source Secure Boot Meets Open Hardware, wolfBoot Integration with TROPIC01 Secure Element, presented by wolfSSL Senior Software Engineer Daniela Lacamera, Tropic Square CEO Jan Plaska, and Solution Engineer Maxim Kostin. My name is Shizuka and I'll be moderating the webinar. All attendees will be in listen-only mode. If you have a question, please use the Q&A box. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. If you'd like to stay updated with all the latest from wolfSSL and Tropic Square, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Also, feel free to email us at fax@wolfssl.com if you have any additional questions. And now I'd like to give a brief company overview before we move to the technical presentation. Today, wolfSSL secure over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by a strong partner network that we are proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, FIPS certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSHV2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrapper, and JSSE support, commercial support for Coral, and our latest product offering, wolfHSM. These offerings are accompanied by slow maintenance and support plan up to the 24/7 level. We also offer full service consulting. And now I'd like to turn it over to Daniela, Jan, and Maxim to discuss open source secure boot meets open hardware, wolfBoot integration with TROPIC01 secure elements.
Thanks, Shizuka, and welcome everyone. Our focus as wolfSSL is security, and we do secure the internet by securing data, and especially we do that through our three main areas of focus, which are securing data at rest, using the cryptography that's offered by wolfCrypt, securing data in transit with SSL, TLS, but not only, also SSH and other higher level protocols such as MQTT, and we do that in over any possible transfer medium, so not just over IP networks, but any channel. And then finally, firmware updates and secure boot, which is the area we'll focus more today by showing the integration between wolfBoot and TROPIC01 from Tropic Square. Shizuka has already introduced the company, and this is our product line. wolfSSL is our flagship product, and it's our lightweight SSL TLS implementation written from scratch back in 2004. And that relies on wolfCrypt, which is our crypto engine. As I mentioned, MQTT and SSH library specific that can scale down to small microcontrollers, a TPM library that helps interfacing with TPM 2.0 devices, PKCS11 engine, HSM, wolfSentry, which is an intrusion detection and protection system for embedded devices, and a few projects that helps us replacing the cryptography in OpenSSL installation, Wolf Engine and Wolf Provider, and wolfBoot, which is our secure bootloader, which is the main topic of today, and that is the main brick of our secure boot and secure firmware updates solutions, and we'll analyze how it works a little bit and how secure boot is important today, and why it is important to interface with other security modules, and especially those that have such a transparent and open design and implementation. We do offer multiple language wrappers to use the libraries from different scenarios and environments, and also a few command line tools that we support and maintain. Of course, testing takes a lot of our effort, and we do have a quite elaborate system of continuous integration, which is hybrid, partly running in cloud and partly running on physical nodes that help us test the products on specific hardware interfaces and targets. And a lot of effort is spent as well on FADS testing in particular, which is very important for security, for testing security software. And we use 6 different FADSers. Some of them have been written from scratch, especially for testing wolfSSL in particular. And so tests happen on a continuous integration on each modification that we make to the software, and also some of them run nightly, longer tests run weekly, and so on. Now to wolfBoot and a bit more information about it. wolfBoot is the open source universal secure bootloader. It's a project that started back in 2018. It is very portable. The first implementation has been done on ARM Cortex-M, but nowadays we do support all the, let's say, most popular architectures, from smallest microcontroller up to x86 64-bit as a BIOS replacement on modern processor like Tiger Lake and Raptor Lake. We do support about 40 different single targets, but also on those platforms where wolfBoot is not directly being ported, it can be run as a library, so just as an add-on on your existing bootloader solution to include the secure boot features that we will see. Since the very beginning, wolfBoot has been designed with safety in mind, so it is not allowed for our development team to place any dynamic allocation in the bootloader, and there is no heap management, basically no IRQ handling unless strictly required by the initialization, so just in a few cases. Everything about the memory and the execution flows is predictable at compile time. And we do have also specific protections against glitch attacks, fault injections, and especially electromagnetic fault injections that might be used against the secure boot procedure to attempt and skip the authenticity check of the actual firmware. So there's some unique features. We do support Delta updates with emergency fallback. So you, instead of sending the new version, the entire new version of the software, you can send a binary patch. We do support end-to-end encryption with Chacha or AES. We do integrate with TPM as well as other hardware security module. And of course, we do inherit some of the features from wolfCrypt itself. So FIPS 140-3 certification, certified cryptography, and also DO178 up to DAL-A for some, for most ciphers that are in use by wolfBoot, which makes DO178C certification for wolfBoot very easy. It is flexible. It is designed to be flexible. wolfBoot can be customized to fit into a specific secure boot use case. It can run as a library, as mentioned. It has multiple key stores and partitions that can be managed. And it can also add custom tag length value fields in the header to integrate extra metadata that you want to include with your firmware distribution or software distribution to be updated. The main goal of Secure Boot, of course, is to prevent running on unauthorized software on board of your own system. So the mechanism of Secure Boot, as described in literature, consists in a secure bootloader that would always refuse to run any non-authentic code. And of course, this code needs to be validated according to the proposed standard. So when we started writing wolfBoot, there was no standard, no advisory RFC, but we were following the effort of a team within the IETF, the SUIT team, SUIT, Software Update for the Internet of Things, which eventually drafted a document that later on became RFC 1919. And this basically consists in the main documented specification for wolfBoot as it mandates small parsers and the usage of a manifest header with metadata and of course the public key based authentication. This is the most important part of the Secure Boot because it's what ensures that only the owner of the private key can sign a valid firmware that can be run on the target. It's the only point of, let's say, management for the security from the key point of view is a single trust anchor, which is used as a root of trust for the authentication of the firmware. And of course, we do have hash-based integrity verification using SHA-2. And the entire process of updating, so the transferring the updates is not part of the tasks of the bootloader, but it's basically assigned to the application, which is in charge of receiving the update from a remote location and storing it into a update partition that will be later on validated and considered for installation by the bootloader. So how this mechanism works, basically we do have tools that we distribute for Windows, Linux and Mac that can be run on everywhere, and they can create keys, import existing keys and sign the firmware. The key pair usually is generated once, as we will see. This means that can be either provisioned in the software or pre-provisioned, for instance, on a secure element. And then this public key is then stored in any of these ways in the target, while the private key stays on the server and it's never shared. So the security only depends on the unique private key that's used to sign the updates. So the private keys, of course, are never distributed. They are stored in your cloud, in your backend, in your HSM. And then when you sign a firmware image, the tool will just attach a manifest header to the image. And this manifest header contains all the signature and the digest, for instance, a signed digest of the image, so that you can verify both the authenticity and the integrity of the image before choosing to boot or choosing to start the installation of the update. Since the firmware version is also part of this verified payload, the firmware version cannot be altered without invalidating the signature. This is very important because wolfBoot will protect against rolling back to a previous version by not allowing the installation of a previous version than a version that has a smaller number than the one that's currently running, to prevent that an attacker might want to downgrade the device to exploit a known vulnerability that has been already fixed. And the other thing, as we said, so the only root to trust requirement is a trust anchor that's required to embed the public key that's used to verify the signature. So sometimes this can be done on a non-volatile memory of some kind, but the obvious best choice, best case scenario is to protect your trust anchor as a root to trust inside a secure element, like the examples that we will show today. So just to recap, the embedded system manufacturer has a trusted firmware. RFC 1919 mandates that this should be signed with a private key and verified on the other side by a public key that can be stored in a key store on the device, and then only then the device is authorized to start the current firmware or start the update. We do have two types of use cases in general. Of course, this, let's say, also split down into other specific use cases. For instance, in a microcontroller devices where all the memory, also for the non-volatile memory, is mapped continuously in physical space. Due to the executing place restriction, we can have boot and update partitions in the same internal flash, or the boot partition on the executing place, and then the update and swap partitions on a secondary flash. The swap partition is typically as big as a single sector and just ensures that the entire process is fail-safe, because there is always a copy available, two copies available of the same sector being copied at that time. So an interrupted procedure of update can be resumed. And in that case, in some microcontrollers, you can use a single registry bit to basically directly swap the logical mapping of two banks of the same internal flash. And this makes the updates basically very, very quick, because you can instantly remap the applications, so the partitions of the two images containing the applications just by flipping a bit in a register. On CPU-based systems, though, we do have a different set of features. So you do usually have an A/B partition scheme. So there is an election that is run at startup. If between those two, which one can be authenticated, the one that has the highest version is going to be staged, but there is no need to move any data there, and because the content of the partitions are usually loaded into RAM before being staged. So this means that we have the two strategies here, either the A/B approach, where you have a non-volatile memory separated into partition with the same hierarchy level, and then you load it into RAM before verifying and staging, and a boot update approach where you usually have to swap the content of a boot partition and update partition. And of course, the A/B approach is only provided for firmware images that are position independent and can be remapped to the same address using, for instance, a VMM, or loading it to RAM to the same address before staging. So after this introduction to wolfBoot and secure boot in general, I will give the floor to Jan that will tell you more about TROPIC01 secure element from Tropic Square.
Thank you, Daniele. Hope you can hear me.
Yes.
Perfect. Hello, everyone. Thank you for joining. And yeah, let's go to the next slide. I will start with introduction about Tropic Square, because actually it might be the first time you hear about a company called Tropic Square. And let me start with explaining the title or the name of Tropic. It's really acronym. It's short for the truly open IC. And that's the reason why we started our operation. So we've been founded in 2020, and in 2025 we are European fabless semiconductor company. We have a secure element device on the market, and really focusing on the security from the, let's say, the original sense of the meaning of the word. Like, it's really security without any compromises. It's really to be truly secure, which means you have to have an auditable and transparent architecture. So it's more like getting the equivalent of open source software at the silicon level, which is obviously a bit tricky, but here we are. So we started in 2020, had the first prototype tape out in 2022. Samples were available in early 2023, and we went through the security testing, through these hackers laboratories to assess side channel resilience and critical features. And then we progressed to designing what we call TROPIC01. And the chip was announced at the Embedded World early this year in March, and we got an award for safety and security. So very proud of it. And let's move to the next slide. Okay, so why Tropic Square even exists? So next slide, please. Yes, this is perfect. Thank you. So, we started to solve the problem with the security when you can't really, or it's very tricky to build secure devices if you have a black box in the system, and the black box are traditional chips. So traditional solution where you don't know the details, and when the products go to the market, then typically issues are discovered by these attackers, which do not follow the data sheets. They do not follow the guidelines used for the security evaluation in the labs, and they just trying to find the weakest point in the design. And unfortunately, they are very successful. So you can see it in the newspapers. So a lot of cybercrime issues, exploits of the undocumented features, which are essentially backdoors, vulnerabilities gets discovered later when the devices are out in the field. And semiconductor reaction is not really fast enough. So the innovation is not really fast enough to cover what we really need to protect, which are the customer data, and also react to the shift in the industry that the devices these days are typically commodities, but what's really important are the data which they consume or generate. And in proxy, they basically protect or endanger end users. And this is then not a new concept. Actually, it's known from Danish cryptographer Kerckhoff, and very popular, Kerckhoff principles stating that basically cryptographic system should be completely transparent. The only thing which you need to protect is the cryptographic key, and that's what we are trying to build at the silicon level. So yeah, we really believe that the security by obscurity is not enough. Obscurity is failing, but certain extent, but not really for the devices and the applications which we need for the decentralized and autonomous future. So our answer or that or solution is the TROPIC01. As I said, first product, open architecture, auditable secure element. We really focus on high physical security of this chip. So there's a lot of detectors, and we will discuss later, like how we take care about that. But also the side channel resilience and fault injection resilience are very high on our priority list. So the device is really designed to be secure when it's powered off or when it's in the operation. And due to the transparency, openness, basically we can claim there are no backdoors or undocumented features. There is no place where this can be hidden in the system. Auditable silicon, utilizing open source and open source chip design, which is quite emerging trend, to be honest. RISC-V and all these things kind of click together and connecting, and our product is one of the demonstration of that. There is some alternative to the for the existing solutions. Okay, hopefully you can see it. So it's a block diagram of our Tropic chip. So as I said, secure element, and it's really the typical architecture, I would say, what you can see there from the let's say functional perspective. So the role of the secure element is really to, let's say, allocate the security critical stuff into the dedicated perimeter. In this case is the chip, which is really a standalone device. And because of that, you have a defined perimeter which you are protecting. And inside this perimeter, you have a trusted execution environment, which means you have a TRNG, you can generate the keys, you can process your cryptographic algorithms, doesn't matter which one it is. And also there's some memories like OTP memory, fuses, something what you can either make sure that it's not really readable like anti-fuse OTP or fuses when you actually, because you follow the auditability, you want to demonstrate, or you can demonstrate that actually particle fuse has been burned and configured according to a specification. Chip consists of the flash memory. We call it like R memory in our documentations, like reversible memory, and yeah, on the middle part, like the yellow secure channel pin verification engine, elliptic curve cryptography, and memory encryption engine. These are the cores which are designed by TROPIC Square, and this is the fully auditable core of the silicon, which will be on the GitHub. Also, the RISC-V CPU and the SPI interface is fully auditable. So SPI interface and RISC-V kind interpret the API and executes the operations on the dedicated hardware accelerators. And on the bottom side of the silicon, you can see the third-party blocks, which essentially creates the infrastructure for building the secure chip, which might be a physically unclonable function, TRNGs, or detectors like EM, electromagnetic detector, glitch detectors, laser fault injection detectors, temperature sensor, and so on. So this is the block diagram, but that's the functionality. In terms of the cryptography, I don't want to go to the details, but we do support Edwards ED25519 and P256 elliptic curve. And what I would like to highlight here is these things on the right-hand side. So basically with the auditability, we really embrace having no undocumented features in the design. Firmware source code has to be known, like understanding, okay, which part of the chip are really running the firmware and which are the hardened, implementation, no firmware, no update. Threat model is super important part because that's really the documentation which explains which parts are fully auditable, which parts are third party with the limited visibility, and how we compensate for this fact in the security model of the silicon. For example, flash memory. Flash memory is the third party block. We can't disclose too much details about implementation, but we protect by the encryption. So data which goes to the memory are always encrypted, and we can talk openly and demonstrate how we do the encryption, memory encryption, and how we construct the keys and so on. So it kind of helps you to be informed about these levels. Test results, openly talking about what has been tested and why, which kind of side channel analysis has been used, or what has been tested and which results. And hardware sources for that. It's very, very important part for these parts, which can be fully open source, like having the open source code or RTL available at the GitHub. So next slide, please. So quickly, I'll go through the applications. Like, the secure element is very, let's say, straightforward dedicated device. So there's no surprise, like typical application silicon root of trust. That's actually the reason why secure elements exist. They are essentially silicon root of trust. And with this device, you can build a secure boot for your host system. You can build the HSM hardware security module, or basically secure element can behave like a HSM at the PCB level as a silicon HSM. And in terms of application, you open or you build the foundation for the digital identity attestation. You have to make sure that the identity cannot be altered. It's cryptographically, there's cryptographically attested and so on. Secure on-chip encrypted storage, cryptographic acceleration, I already mentioned. Market segments, it's a bunch of the applications, like we can talk like next-gen IoTs, everyone is in IoT, right? So crypto hardware wallets, it's a special segment because actually our company was built with the crypto hardware wallet background, and we coming from this industry, so it's very, very special segment for us. Medical devices, digital identity, automotive, access management. We really early on the market, but we're looking for the application segments, and although you might call it differently, a lot of stuff goes back to this root of trust, identity, and the compliance with the CRA and similar stuff we will be talking later. Okay, for TROPIC01 evaluation, we welcome our early customers to start play with the chip, and we believe the integration is very straightforward, very easy in terms of the electrical wiring. It's already main interface, application interface is 4-wire SPI, so you can easily hook up to any host MCU. And we do have some examples for STMicro on the GitHub. libTropic is our API SDK. So the user interface for the chip is already ready-made for integration to your application. And to support popular platform, we have a RP, Raspberry Pi, header, Arduino Micro E extension boards available. You can see some of them on the pictures. And libTropic utility is also available on the GitHub. So it's really the application which you can run from your Linux console, easily connect with the USB dongle and experience the functionality of the TROPIC01. And typical example is you can generate random numbers. You can generate the cryptographic keys. In the asymmetric crypto, you can get the public back to your system and start playing with this. It's really meant for the demonstration and showing how to use the chip and enabling customers for their application and integrations. Okay, in terms of resources, I would say the most important part is probably our tropicsquare.com website, and you should be able to find all the resources, contacts, and everything necessary. We definitely encourage you to talk to us directly. And on the github.com/tropicsquare, another resource where you find everything. Support portal, support.tropicsquare.com. We really invite you to ask questions and evaluate the chip. You can find a link on the website to get the samples, and we are more than happy to support you in your application and customization of the Tropic chip to your particular needs. TROPIC01 data brief on the website or data sheet straight on the GitHub. And I guess with that, I will hand over to my colleague Maxim.
Yeah. Hello, everyone. So I'm gonna tell you a bit more about some practical aspects of the integration. So I would say that's time for some practical exercises. So I'm gonna share my screen. Here, yeah. So first of all, I would like to say a few words about the role of secure element, specifically TROPIC01 in the secure boot solutions for the embedded systems. So that's in general, we always say that we provide a hardware root of trust. But to be more specific, so that's one of the most important function is providing of storage for the immutable public keys, which is a crucial component for the signature verification. As well as secure storage for AES keys, which are normally used for the images decryption, but it's a sort of optional ability. Important to say that secure element and TROPIC01 allows to do some secure provisioning independently of customization of the main or targeted MCU or MPU board. So that's keys might be injected or installed even in different locations than the main board could be flashed or customized. Also, that's possible to store some associated data like seed or IV data in secure memory and immutable memory as well, which might be also useful for some application. And potentially, we can implement functionality like signature verification with the TROPIC01 internal engine. We have quite a bigger storage space, flash size, I mean, and we can even store part or even entire bootloader images like first step or second step bootloaders. And in theory, we also can support decryption of some host firmware images, files, or some data objects. Now, I'm gonna say that I'm pretty happy to officially say that we finalized integration recently. That we finalized integration with the wolfSSL, and that's TROPIC01 components software is available on official wolfSSL GitHub. You can see link here. And integration was done through the mechanism which is called the crypto callbacks. So that's a set of functions we implemented, and here just you see the list of functions which are already available, and we count to make this list longer in the near future. So that's just a few words, so that we can provide the support of random number generation, seed generation, Edward curve key generation, sign-in verification, and as well as AES, GCM, and CPC encryption and decryption. TROPIC01 port exposes 4 main functions to wolfSSL. These functions might be also used by an application like secure boot, for example. That's what I will show later. So that's the most initial function. It's definitely TROPIC01 init. That's in the case if you needed to close session. That's you needed to call dinit. Set pairing keys is a rather important function because that's possible to replace default pairing keys with some vendor keys, or maybe even some keys generated by operator. So that's, and the cryptosystem, actually this is a function which explicitly implement crypto callbacks. So that's quite important information that we have reserved some slots in our secure memory for different types of objects like AES keys and ED 25519 public and private keys. That's important to follow this allocation scheme just to be compatible with the provisioning of the keys. So that's first of all, that's if you want to use Tropic secure element, you needed to build a TROPIC01 SDK, which is also known like libtropic. This SDK is available on our GitHub, github.com/tropic_/libtropic. So that's and it's a pretty straightforward process how to build it. Important that we normally use CMake build system, but any other build systems are also possible. So this is just options for our users, our customers. So to build wolfSSL with the TROPIC01, that's you also needed to follow some standard procedures, standard steps. So just to use, we would recommend to use autoconf and configure tools. Important to use options like with the TROPIC01, enable cryptosystem and enable ED 25519. So that's this is again quite a straightforward process how to build wolfSSL with the pre-integrated TROPIC01 crypto callbacks. Here you can see that's some example of the way how to implement wolfBoot. That's using TROPIC01 port and crypto callbacks, and as well as libtropic like interface to the physical chip TROPIC01. And that's the sequence start with the TROPIC01 init function, which will trigger internal function of libtropical init, and this will establish secure session with a secure element over SPI interface. So, and also this secure session established so that it's possible to request different operations or different data objects, and specifically in the case of wolfBoot, we use our data memory read just to get back our memory object, which is actually that's public key. So that's this public key is used by wolfcrypt for the verification of the signature of the digest of some firmware image. So it's quite a simplified view on the implementation. But for in a case if you need some clarification, we always welcome that for any questions later on. So and now just I would like to show some demo. Okay, now I'm gonna show you some demo, which is supposed to be a good example of how the combination of wolfSSL open source software and the TROPIC01 auditable secure element might be used as a hardware root of trust and secure storage for some use cases like secure boot, secure firmware update, and the basic HSM. Our demo consists of several components. The popular targeted board STM 32F439 nuclear with the TROPIC01 Arduino shield, which is plugged into the Arduino socket of the STM board. Actually, this is the main targeted device where we need to implement secure boot loading. To make it happen, we needed to have an option to sign the firmware or application image with the proper private key. For that, we will use a TROPIC01 USB dongle connected to Linux PC and a basic HSM application, which provides a convenient way to initiate different functions. You can see UI of this application in the top right corner of your screen. Source code is also available at github.com/tropicsquare. At the bottom of the screen, you should also see the serial output from the targeted board. It's important to say that TROPIC01 chip, which is connected to the STM board now, already has some pre-provisioned public key, which was stored in one of the internal ECC slots. This provisioning might be done at the production stage as well as later on. Specifically for this demo, we have installed the key in a slot O using a dedicated firmware image for the STM32 board. So, at the first step, we will need to flash the factory image into the STM32 board. This factory image contains the wolfBoot code at the start address as an initial bootloader. This bootloader communicates with the TROPIC01 via SPI interface, getting the public key, which is used further for the validation of the signature of the application image. In a case of successful verification, the wolfBoot will jump to dedicated address in the flash memory, and the main application will be running. If the signature verification fails, wolfBoot will go to the alarm mode and will prevent any further loading. So now I'm gonna click on a flash factory image, and we will follow output of the serial terminal as well as blinking LED on STM board. As you can see that LED is blinking, it means the flashing is going on. And now let's wait for the output. It takes a few seconds. And now we can see that the signature was verified and application loaded successfully. So now we will try to generate a new ECC key pair with the TROPIC01. Let's for that, I'm gonna click on Generate Keys button, and please take a look on a red LED of USB dongle. If it's blinking, it means operations are done within the TROPIC01. Okay, great. ECC key pairs were generated and stored. So that's now actually we can also export generated public key only because the private key never leaves the secure memory of TROPIC01. Also, we can generate and securely store AES keys, which might be used for the image encryption and decryption. But this is out of the scope of this demo and might be a good topic for one of our next webinars. So, since ACC keys are ready, we can use a private key to sign the application image. For that, we can preloaded, pre-uploaded firmware image with the application, with the demo application made specifically for this event. So that's now we need to calculate hash digest over this image and sign this digest with the private key we just generated and stored in the TROPIC01 memory. So the image was successfully signed and we can flash it into the targeted board. For that, I'm clicking on Flash Sign It Image button. We see that the flashing is going. Okay. So since we have a new private key used for the signing the image, which doesn't correspond to the public key stored in the targeted board, the signature verification fails, and wolfBoot prevents any further boot loading. So now we will try to sign the image with the correct private key stored in some file or maybe in another slot of TROPIC01. For this demo, we will use some predefined key, pre-generated key set, which contains both a private and public key. So we save those keys to the TROPIC01. Okay, and now we're ready to repeat the same steps like before. So calculate hash. Actually, we use the same application image like before. Then we needed to sign this image. And now we can flash sign it image again. So here we can see the correct booting process because the image was signed with the correct private key. I hope that this demo gave you an overview on how to use the combination of a TROPIC01 secure element and wolfSSL software for the sign-in firmware images, handling key management and implementing the secure function. Thank you. Okay, now I'm gonna show you some demo.
Yeah, you want to go ahead, Maxime, with the presentation? Well, very quickly, I will right. So Maxime, wait, you want to summarize what you just shown?
Actually, yeah, that's final sentences. So that's regarding our further plans. So that we expect to implement other crypto callbacks functions and support some other applications and use cases provided by wolfSSL. Actually, that's it from my side. Thank you.
Okay. Thanks, Maxime. So yeah, we'll spend a few words on why secure boots and where is this coming from, especially from the landscape of the regulatory landscape. You probably know that Europe has already started the CRA regulation 2024-2847. Which mandates cryptographic verification of firmware at the boot stage. So that's the exact feature we have shown today. And this is already in force for new products and will be started to be enforced properly as product compliance requirement before the end of 2027. But CRA is not the only regulation. As you can see, Also, there are other frameworks around the world that starting to demand boot integrity and authenticity. So we do recommend our existing customers, our existing users of wolfSSL to think about secure boot and how to meet those regulations for their product in their specific verticals with the different requirements. And we help our customers to meet those because those technical requirements, as you have seen, coincide with what we offer right now, which is firmware verification as boot with integrity, authenticity, secure update mechanism. We roll back in time, and we do facilitate SBOM and vulnerability management thanks to our active traceability of all the components and CV tracking, and the fact that wolfBoot has a single dependency in wolfscript itself, and it's basically a leaf item in your SBOM, and we do have a track record of CVE tracking and openly disclosing all the vulnerabilities we find and fix according to the CVE tracking. So the design highlights is of wolfBoot, how it simplifies the process of compliance. We have a minimalist and portable architecture. We have our abstraction layers that can basically work on all ported integrated MCUs and system on chips, and can also run as a library on those that are not directly ported. We have a configurable crypto backend that can include, as you have seen today, separate HSMs, and can integrate also with the software available from wolfscript all the classic algorithms from CDSA, RSA, but also post-quantum algorithms like LMS, HSS, XMSS, and MLDSA, and even supports hybrid secure boot, which combines classical and post-quantum cryptography for the best-in-class, let's say, switching path towards post-quantum safe cryptography. And that means that, let's say, we guarantee that your TRA requirements are covered from the point of view of firmware signing and authentication, and we do provide all the support and documentation that needs that might be needed to customize use cases and specific ports. And this concludes basically our presentations for today, and we are happy to reply to the questions that you have asked through the Q&A.
Thank you, Daniela, Jan, and Maxim. So there's one question. Is ECDSA Corb SECP 256K1 supported by TROPIC01?
You know, you want to take
So Shizuka, can you repeat the curve? I didn't catch that.
Yeah, so the question is ECDSA Corb SECP 256K1 supported by TROPIC01?
Yes, that's correct. Yeah.
Okay, perfect.
It is supported, yeah. Okay.
And there is another question. What is the default?
What is the default?
Mm-hmm.
Default.
Well, I don't know the context of this one, but there is no default for wolfBoot on the cryptographic algorithm. You can choose among ED25519, ED448, ECC with the curve you just mentioned, so SECP 256, 384 and 521, RSA up to 4K, and the post-quantum algorithms I've mentioned in the previous slide. And also you can combine two of those together. As you've seen, there is an overlap with the curves and the algorithms supported by TROPIC01. I believe that the demo today was shown with the ECC256. Is that correct, Maxim?
It was an Edward curve, AD255.
Okay,
Yeah,
AD25519. Okay, okay. But it's just to mention that it is interchangeable. It's just a matter of changing the configuration there.
Yeah, that's from that perspective, we can definitely support different curves, because we provide some sort of secure storage so that we can store keys from different curves.
So even of curves, so you don't support, you can still act as a root of trust, for instance, for a post-quantum key store that your secure element doesn't use directly, but still provides support as a trust anchor.
Exactly.
Yeah, that's right. And actually, I'd like to make a correction about the first answer, because I think it was the SecP256K one. Yeah, Bitcoin curve was the question. And actually,
Okay.
if it was Bitcoin curve, it's not by default supported by TROPIC01, as it's not like hardware accelerated. And we have a lot of internal discussion like how we can enable by firmware update, but it's not currently in the product. So sorry for that.
But it's supported. It's available through software using wolfScript. In that case, of course, it won't be hardware accelerated, but there is still a fallback in that case for a solution like this. Let's say, if you really need to use that curve.
Okay. And there is another question. What about native support in U-boot? Is it necessary to use the wolfBoot library?
We have written a lot about this in our blog section on our website. So there are different ways of combining in a boot chain U-boot and wolfBoot. So one way would be, of course, to have wolfBoot as a first stage, for instance, and authenticate U-boot. And this also gives you the possibility to do a secure update of U-boot itself. Eventually, U-boot is a very large bootloader, and whose first, let's say, goal is not to secure your boot process, but it has many more features than just wolfBoot can offer. Let's say, because wolfBoot has a different focus. Let's say it doesn't have any user interaction. It doesn't have partitions to store configuration items. It doesn't have the possibility to access any network device. And this is by choice, by design, to reduce the attack surface as much as possible, where secure boot is actually critical part of the process. The solution that the question is suggesting of integrating wolfBoot as a library within U-boot is definitely possible. Of course, there are things to be considered, and the fact that U-boot might change its behavior at runtime, so it might not be the most secure strategy from the architectural point of view, but this might definitely work because you just add one extra step to U-boot to, let's say, authenticate verify the integrity and authenticity of the kernel image. For instance, you have to stage afterwards before staging it and refusing to boot if that doesn't work. But of course, that would require U-boot that's configured as minimalist as possible, again, to make sure that the surface of attack stays as small as possible. So probably what I would suggest and what we have done in the past is either replacing U-boot completely if U-boot was only used, for instance, for features that are available in wolfBoot, like the election of the image during an update, if those are the only features that you need. Otherwise, the most so using it as a second stage bootloader. Otherwise, if you can't really, let's say, live without some features of U-boot, but very interesting questions indeed. We do like U-boot, and we have explored the relationship with U-boot in many different projects so far.
Awesome.
Daniel, sorry, Daniel, just one idea, just maybe could it possible to use a wolfCrypt instead of wolfBoot in a U-boot, like just a crypto engine.
Sure, but the advantage of using wolfBoot as a library instead of just raw wolfCrypt is that wolfBoot also comes with the sign tool, the keygen tool, and it already has, let's say, an infrastructure of manifest header, versioning, and all these things that come for free if you're using basically wolfBoot as a library. And the interface is quite straightforward. You have a verify integrity and a verify authenticity over anything. So it can be loaded in memory or fetched from a non-volatile memory somewhere, and you get the same functionalities, but on top of that, you can also use the host tools.
Yeah, just want to add that in all of those cases, you can also use a TROPIC01 like supporting element thanks to this crypto callbacks. So that's in the.
Of course, yeah. That's everything is layered in a way that
exactly,
you can still use wolfBoot as a library or in any context or in any recipe, let's say, if you want, or as an integration of a different bootloader. Still, the crypto operations can be remapped to use TROPIC01 in any case.
Yeah.
As well as Maxime shown today, you can also float the sign operations and even hold the private key on the other side, thanks to integration with our signing tools. That doesn't require any code modifications. It can be done in 3 steps, basically.
Awesome. I think those actually, I do have a following question. Regarding the ECDS 2K1 question, does implementing 2K1 by setting values in firmware change the logical determinism property of the signature? The speed of hardware acceleration isn't needed, but the determinism is.
Yeah, I would suggest to go to talk to us directly, and we can look at this in detail. Definitely, one of the issue we discuss is like the performance of the signing in the Bitcoin curve when it's not really relying full hardware acceleration, only firmware implementation. And we will double check the other question about the determinism. I don't want to, I want to be correct. Yeah.
Perfect.
Thank you for the question. Yeah, appreciate
but definitely.
that.
Definitely, this is a very interesting question. So that's something we can discuss later on.
Perfect. Thank you. I think those are all the question I have. Thank you, Daniela, Jen, and Maxim for hosting an informative webinar. Thank you, everyone, for joining the webinar today. You can keep up with our upcoming event, meet our team in person, read our blog posts, and get the latest wolfSSL and Tropic Square update by following us on X, connecting with us on LinkedIn, and subscribe to our YouTube channel. If you have any question, please reach out to us at fax@wolfSSL.com. And thank you.
Thank you very much.
Thank you very much.